I have to admit, when I first saw the topic for this deep dive, my brain did that thing where it just, tries to go into screensaver mode.
Let me guess. The words object-oriented programming don't exactly scream thrill ride.
They really don't.
Mm.
It sounds like the kind of thing you learn in a basement lab with, like no windows.
Hmm.
But, and this is a big but, once I started reading through the stack of research you brought, I realized I was completely wrong.
Ah.
This isn't really about code, is it? I mean, sure, it's about software, but the underlying concept feels much more philosophical.
That is the best way to approach it. If you strip away the syntax and, the semicolons, object-oriented programming, or OOP, is really a story about how we try to organize reality.
To categorize the chaos.
Exactly. An attempt to categorize the chaos of the world so that we can, well, control it.
And it's an attempt that completely took over the world. We should probably establish the stakes here. If you are listening to this and you used a smartphone today or an ATM or even just opened a web browser,
Yeah.
you are navigating a world built by OOP, without a doubt.
Right. It has been the dominant paradigm for software engineering for the last 30, maybe 40 years. Java, C++, Python, the languages that run our modern infrastructure, they're all built on this foundation.
And this is why we're doing this now.
Right.
There's a growing sense that we might have bet the farm on the wrong horse.
That's the dramatic arc. We have the rise, the absolute dominance, and now, well, the critique.
That's the part that hooked me. We went from this utopian idea of code behaving like biological cells to a reality where, and I love this visual, we have gorillas holding bananas and everything is just a mess.
It's quite a journey.
So let's go back to the start, the before times. Because I tend to think of early computing as just math, a list of instructions. Do step A, then step B.
That's exactly what it was. It was procedural. Think of it like a recipe.
Okay.
Crack egg, whisk egg, heat pan. It's a linear list of verbs. And that works perfectly fine if you're calculating a missile trajectory or, say, doing a tax return.
But the world isn't a list of instructions. The world is full of things.
Precisely. And that realization didn't happen in Silicon Valley. It happened in Norway in the 1960s with a language called Simula.
Simula. The name kind of gives the game away.
It does. It was designed for simulation. Specifically, the researchers were trying to model these really complex physical systems like ships moving through a busy port. Imagine trying to write a linear recipe for a port.
You can't. It's impossible. You have a ship arriving, a crane that breaks down, a truck waiting. It's all happening at once. It's not a list. It's a swarm.
Exactly. So the creators of Simula had this radical idea. They said, stop writing a list for the whole system. Instead, let's create a virtual ship. Let's create a virtual crane.
They made digital actors.
Yes, they called them objects. And this is the crucial shift. The virtual ship isn't just data. It has its own internal state. It knows its cargo capacity, its speed, and it has its own behavior. It knows how to dock.
So instead of a central brain controlling everything, you just wind up these little toys and let them interact.
That is the birth of the paradigm. You model the problem by creating objects that mirror the real world.
And this leads us to Alan Kay. He's all over the notes. He created Smalltalk at Xerox PRC, which is, legendary. But what struck me was his mindset. He wasn't looking at these things as data structures.
No, not at all. Alan Kay is a fascinating figure. He had a background in biology, and he looked at a computer program and thought, this should work like a living organism.
The biological cell analogy.
Think about your body. You have a liver cell and a heart cell. They are totally independent. The liver cell doesn't reach inside the heart cell and start, tweaking the valves.
That would be catastrophic.
It would kill you. Instead, they send chemical messages. Signals. Kay envisioned software as a trillion little computer cells floating on a network, communicating only by polite messages. Could you please update your display? Here is the data you asked for.
It sounds so elegant, almost democratic. Every object is its own sovereign state.
It was a beautiful vision, but there's a big gap between a vision in a research lab and a technology that runs the global economy.
So how did we get from Norwegian ships and biological cells to OP being the default way everyone writes code? The notes mention the 80s and 90s, and specifically the rise of the GUI.
The graphical user interface. This is the connection that people often miss. Think about the transition from MS-DOS, where you just typed commands on a black screen, to Windows or Macintosh.
Okay, I'm picturing it. On the black screen, I'm typing verbs. Print. Copy. It's procedural.
But on a desktop, You see a file folder. You see a trash can. You see a window.
Those are nouns. Those are objects.
Oh, you see, the interface itself became object-oriented.
Go on.
When you are building a system where a user drags a file into a folder, it makes infinitely more sense to write your code in objects, too. You create a window class. It has a height, a width, a color. It has behaviors like open, close, minimize.
So OOP won because it mapped perfectly to the visual metaphor we were all learning.
It was a hand-in-glove fit. You couldn't build the complexity of Windows 95 efficiently using old-school procedural lists. You needed to organize the code into these neat little boxes.
Okay, so that's the why. But we need to talk about the how. Because the sources list 3 big pillars of OOP. And these terms, encapsulation, inheritance, polymorphism, they sound like wizard spells.
They are the holy trinity of the paradigm. If you take a Computer Science 101 class, you memorize these.
Let's start with encapsulation. The sources sometimes call this information hiding, which frankly sounds a bit suspicious.
It is keeping secrets, but for your own protection. Think about the car you drive.
Okay,
When you want to accelerate, what do?
I press the gas pedal.
Do you manually adjust the fuel-to-air ratio in the injection valves? Do you synchronize the spark plugs?
No, definitely not. I would explode the engine.
That is encapsulation. The car object hides the messy, complex state of the engine behind a simple public interface, the pedal.
So in code, an object just puts a wall around its data.
Yes. It says, nobody touches my internal variables. If you want to change something, you have to ask me through a method, like set speed.
And the benefit is safety.
Safety and sanity, we call it decoupling. It means I can completely redesign the engine change, how the fuel injection works, and as long as I leave the pedal alone, you, the driver, don't need to learn anything new. The rest of the system doesn't break.
That makes sense. It stops that spaghetti effect where pulling one thread unravels the whole sweater.
Exactly.
Okay, pillar 2, inheritance. The family tree.
This is the feature that really sold OOP to businesses because it promised to save time. It's all about not repeating yourself.
So walk me through the example. We have a person.
You write a class called person, you give it a name and an age, you write the code to check the age isn't negative, maybe format the name, you test it, it works.
Great. Now I need to hire them.
So you need an employee. Now an employee is a person. So instead of rewriting all that code for names and ages, you just say class employee inherits from class person.
And boom, it just downloads the DNA.
Instantly. The employee has a name and age. You didn't type a line of code for it. Then you just add the new stuff. Salary, job title.
It sounds so efficient.
Oh,
I can see why managers love this. We're reusing code. We're building on what we already have.
it creates a taxonomy, a hierarchy. Animal, mammal down, dog down, poodle. Everything has its place.
Which brings us to the third one, the one with the hardest name, polymorphism.
Many forms. This is usually the stumbling block for students, but it's actually the coolest part.
The source material uses the shape example. I remember staring at this in a textbook once. You have a list of shapes, circles, squares, triangles.
Oh, right. And you want to draw them on the screen. Now, mathematically, drawing a circle is totally different from drawing a square. Different formulas.
So without polymorphism, my main program would have to be this mess of if statements. If it's a circle, do this. If it's a square, do that.
And every time you invented a new shape, like a hexagon, you'd have to go back and rewrite your main program. It's brittle.
So polymorphism lets the main program be blind.
Deliberately blind. The main program just looks at the list and says, I don't know what you all are, but I know you are shapes. So, de-draw.
And the circle hears draw and runs its circle code. The square hears draw and runs its square code.
That's it. It's called dynamic dispatch. The object decides how to interpret the message. Your main system can stay simple and clean even as you add more and more complexity.
It sounds like a dream. We have safe encapsulated boxes. We have efficient family trees. We have smart objects. And to help us build this, we even have a manual, the Gang of Four.
Yes. Not a political faction. It's the nickname for the 4 authors of the most famous book in software engineering, Design Patterns.
Published in 1994. Why was this book such a big deal?
Because before 94, everyone was kind of making it up as they went along. The Gang of 4 looked at all this OOP code and said, hey, we keep seeing the same problems and the same solutions. They cataloged 23 of them. They called them patterns.
A cookbook for code problems.
Exactly. Like the singleton, you have a problem. You need one central configuration for your app. You don't want 5 different config files floating around.
So you use the singleton pattern. It forces the code to only ever create one instance.
Or the factory. It gave developers a shared vocabulary. Instead of explaining a complex idea for 10 minutes, I could just say to you, use a facade here, and you'd know exactly what I meant.
So, up until this point in our deep dive, OOP is winning. It's logical, it's structured, it mimics the real world, but
Here comes the but.
the section in the research labeled the critique. And this isn't just a few people grumbling, this feels like a full-blown rebellion.
It is. After 40 years of dominance, we're starting to see where the model breaks down.
Let's start with the gorilla. This is a quote from Joe Armstrong, the creator of Erlang. I absolutely love this imagery.
It's a classic, he said. The problem with object-oriented languages is they've got all this implicit environment that they carry around with them. You wanted a banana, but what you got was a gorilla holding the banana and the entire jungle.
It paints quite a picture. What does he actually mean by that? Because I just wanted the banana.
He's talking about the dark side of inheritance, that family tree we just praised.
Okay.
Let's say you're working on a new project, and you see a piece of code in an old project that does exactly what you need. A little utility function. That's the banana.
Great. Copy and paste.
But you can't, because that function is inside a monkey class. And the monkey class inherits from primate, and primate inherits from animal, and animal relies on biological entity.
So to use that one little function, I have to drag in this massive chain of parents and grandparents that I don't even need.
You have to import the whole jungle. It creates what we call tight coupling. Instead of reusable Lego bricks, you have this fused mass of code that is very hard to pull apart.
So the promise of reuse turned out to be a bit of a myth.
In practice. Often, yes. It's often easier to just rewrite the banana than to try and get it away from the gorilla.
Wow. That's a huge blow to the efficiency argument. But there's a deeper critique, too, right? It challenges the whole real-world philosophy.
This is the philosophical split. You have people like Richard Hickey, the creator of Clojure. He argues that OOP is actually a terrible model of reality.
Why? Real life has objects. I'm holding a mug. That's an object.
You are. But does the mug change?
Well, the coffee inside gets cold.
Right. But in OOP, we try to lock state inside the object. We say the mug owns its temperature. Hickey argues that in the real world, state is just a snapshot of information at a specific time. Real systems are about information flowing, not little boxes guarding their secrets.
So he thinks OOP is too rigid.
Almost cartoonish. It simplifies the world into these neat nouns and categories that don't actually exist, and that leads to the circle-ellipse problem.
Oh man, I read this section 3 times. It broke my brain a little.
It's a fantastic logic trap.
Okay, so geometrically, a circle is an ellipse, right? It's just a special case.
Correct. In math class, a circle is a subset of ellipse. So in OOP, it makes sense. You make circle a subclass of ellipse, it inherits everything.
Seems logical.
But wait, an ellipse has a behavior. Stretch. You can stretch an ellipse along one axis and it becomes a longer, flatter oval.
Okay.
But if you take a circle and you stretch it, is it still a circle?
No, it's an oval.
So the circle class cannot inherit the stretch behavior from its parent without stopping being a circle.
It breaks its own definition.
It breaks the code. This shows that our human linguistic categories, a circle is an ellipse, don't always map cleanly to software logic. OOP forces us into these rigid hierarchies that reality just refuses to fit into.
That's a fundamental flaw. That's a practical problem too, right, with hardware.
That is the final nail. When Simula was written, computers had one processor, one brain doing one thing at a time. Today, your phone has 8 cores. Servers have hundreds.
And OP doesn't like that.
OOP hates that. Remember encapsulation. The object hides its data. I control my state.
Right.
Well, what happens when 5 different processors try to talk to that object at the exact same time?
It's like 5 people trying to drive the car at once.
Chaos, race conditions, data corruption. Because the object is trying to protect its state, you have to add all these locks and complex mechanisms to stop the processors from fighting. It gets incredibly slow and buggy.
So the very thing that made it safe hiding the state makes it dangerous for modern parallel computing.
Precisely. Functional languages, which separate data from behavior, handle this swarm of activity much better. They don't have gorillas holding bananas. They just have the banana, which is data, and the peeling action, which is a function, as separate things.
So where does this leave us? Is OOP dead?
No, absolutely not. It's not dead, but it is evolving, or maybe shrinking back to where it fits best.
The notes mention a shift toward composition over inheritance. What does that mean?
It's the modern answer to the gorilla problem.
Mhm.
Instead of building deep family trees, grandparent, parent, child, you build objects out of Lego bricks.
Explain.
Take that employee again. Instead of saying an employee is a person, you say an employee has a person component.
So I just plug the person brick into the employee brick.
Yes. And if the employee needs to fly, you don't inherit from Bird. You just plug in a flight component.
You only take what you need. No jungle.
Exactly. You see this in modern languages like Go and Rust. They are moving away from the rigid taxonomies of the 90s toward this flexible component-based approach.
So we are deconstructing the monoliths.
We are. Rob Pike, one of the creators of Go, famously called OOP the Roman numerals of computing.
Ouch. That is a burn.
It is, but think about it. Roman numerals work. You can count sheep with them, you can build roads, but try doing calculus with Roman numerals.
It's a mess. You can't.
It's the wrong tool for that level of complexity. OOP was the perfect tool for the 90s, for building GUIs, for organizing teams, but for the 2030s, for AI, for massive distributed systems, it might be the wrong motivation.
That is a lot to process. We started with ships in a port, built a biological computer, got lost in a jungle with a gorilla, and now we realized we might be doing calculus with Roman numerals.
It's the journey of technology. Every solution eventually becomes the next problem.
So, here's the thought to leave you with. If OOP was designed to model the real world, but the real world of computing has moved on to massive parallelism and fluid data, are we holding on to a map for a territory that doesn't exist anymore?
That is the question every software architect needs to ask themselves today.
Something to think about the next time you click a button on a screen. Thanks for diving deep with us.
Thank you.
See you in the next one.